Each month. Simply because you sell people are not professional traders. Hi, this is the world's top sales trader, Jason Evans. I'm going to give you a free 45-minute video of your sales training techniques that will increase your monthly sales in a day guaranteed.
Hey, Chris Center, can you mute yourself? Thanks, Chris.
All right. Great to see you, David, and welcome everyone.
Hi, Ahmed. How are you today?
Good, good. How are you?
Good. Looking forward to the holidays here.
Yes.
Morning, guys. Ramki here.
Hello, Ramki.
Hi, Ramki.
Hey there. How are you, David?
Very good, thank you.
Morning, Ahmed. How are you?
Good, good. How are you?
Not too bad.
All right. So I think we have enough critical mass, and this is basically the call number 90. So again, welcome everyone to another OCP TAP session. And today we have David Chandler from Microchip. And as usual, we go with a format introducing David. So David got his Bachelor of Science in Applied Engineering Physics from Cornell University and MEng in Electrical Engineering from Pennsylvania State University. And after serving in the U.S. Army, David joined the McCoy Electronics in 1996, which through various acquisition is now part of Microchip Technologies, like fish, like during his tenure, he has worked as an engineer and product line manager for various frequency control products. He's currently the senior product line manager for atomic system clocks, including cesium standards and hydrogen masers in the frequency and time system business unit. I mean, it sounds like a dream job, right? So
It's a lot of fun.
yeah, indeed. So today's talk is about quantum theory in action for 80 years and counting. And with no further ado, David, the floor is yours.
Okay, thanks. So thank you for the introduction, Ahmed. I'll go ahead and start talking. So no reason to do the introduction. You already did that. Basically, what I just wanted to bring out, if we look today, quantum applications are all over the news. We keep hearing about quantum computers and quantum communications, and really the benefits of massive processing capabilities and undecipherable communications are what's driving a lot of that. You hear a lot of these buzzwords: qubits, superposition, entanglement, interference, quantum keys. I'll get into a couple of those. But what I did want to point out is, it almost seems like there's a mass amnesia in the media today, because quantum's been around for a long time, as opposed to the news. I'll talk about the old. People using quantum applications or quantum mechanics literally since Bunsen lighted his first burner. He was doing mass spectroscopy, right? Didn't even know that it was quantum mechanics at the time. But since 1860, there's been all these different applications of it. Electron microscopes, which take advantage of the wave nature of electrons, were done in 1901. The first atomic clocks were 1944. They got good enough to start adding as references to national time standards in the late 50s. Solar cells use the photovoltaic effect, which is really just absorbing momentum from a photon to knocking an electron out of a piece of foil. Lasers, which use stimulated emission, which I'll talk about laser quantum applications. Visible LEDs are just examples of a quantum event where you have an electron falling from a valence cell, falling from the conduction band down to the valence band and emitting a photon. And MRIs are also out there where we force the magnetic spin of the nucleus to go in one direction, and then we watch it fluoresce as it relaxes. So it's really just a difference in the applications. We talk about these quantum technologies, quantum computing and quantum communications. But the technology's been employed for a while, and actually we're using technologies from a lot of these other industries in those today. I'm not going to go over Schrodinger's wave equation. We could be here for 8 hours and everybody would still be lost. But the bottom line is it just basically says that the position and the velocity of a particle or energy is defined by this wave equation, and it progresses over time. And what comes out of this are a whole bunch of things like energy and matter are both, exhibit finite indivisible packets, right? So if I look at the atom over here, you can see where the electrons are essentially stuck on one shell. There's, very high probability they're in one area and they need energy to move to the other shells. There's a wave particle duality, right? Any, light can be a wave or a particle, it can be a photon. And same thing with an electron. Even a proton has wave properties to it. Next things that make it interesting for quantum computing are this superposition theory. If you think about a classical computer, we have a 0-bit and a 1-bit, and a bit can't be both at the same time. It's either one or the other. But in quantum mechanics, they truly exist as, a 1 and a 0 at the same time. And until we measure that, we can do calculations all day long and simulate and model all the math to, essentially have this as a superposition of those two vectors. We have to deal with uncertainty, right? Quantum mechanics doesn't ever get precise. If you look at position and velocity, you can't uniquely know either of them, right? You have a certain amount of uncertainty, and as you sharpen one, the other one gets loose. You know less about the other one. Then you get into the other interesting thing, which is entanglement, which is two-particle interaction, interdependency, right? Basically, there's a relation between these things. If I measure one, the other one could be on the other side of the universe. And as soon as I do the measurement of one, it's going to force the other one to, be in that state. Almost sounds like, problem with the theory of relativity exceeds the speed of light, but lots of experiments have shown that's actually what's going on. Then we have this thing called the measurement effect, right? It can be in a superposition of states, but the moment you measure it, it collapses into one of those two bits. So this is kind of like talking about Schrodinger's. You're basically, cat's in the box, it's dead or alive. You open the box, it's in one of those states after them. And then finally, another issue with quantum mechanics that helps with quantum computing is interference. So because of the wave-like nature, you can have interaction, either destructive or constructive interference, right? So it makes some probabilities very unlikely, even though intuitively it may not make sense to us in the classical realm, and other ones very, very likely, even though it doesn't jump out to us. And we'll cover how it plays in as well. So how do quantum computers use this, right? Why are they there? Why are we talking about this? Well, it's because the unique math that was created to work with quantum mechanics turns out to have some really interesting properties to solve complex problems. And those problems, some of them would require years for current supercomputers to complete them. And others may be unsolvable with current traditional computers. There's all this theory about different types of equations, problems, and how you can solve them. I think the argument's out as to whether you actually can solve completely unsolvable, but the possibility's there. But anyway, the type of problem, and it's not every problem, by the way, but the type of problem it can solve very, very quickly is something like factoring a very large number, right? So that is basically something a quantum computer can do exponentially faster than a classical computer can do. And that's the type of problem that's driving people to really start focusing on. So how do we realize a quantum computer, right? I mean, how do we effectively use superposition, entanglement, interference, and measurements? Well, basically what people turn to, at least one of the solutions, is to actually use quantum physics, right? So you use the actual quantum particles as your calculator or as your computer. You're basically using individual ions as these qubits or bits that are going to be either 1 or 0. And then we use electromagnetic fields and microwaves in the form of microwaves and lasers to essentially prepare the element, whether or the particle, perform logic operations in what we call quantum logic gates, which is forcing it between states and then measuring it at the end. By the way, if this sounds awfully similar to you, this is a cesium beam tube, right? Which ultimately, I think it's a stretch to call it a quantum computer, but it's at least a series of single bit gates. If you look at it from left to right, and I'll explain how it works in a little more detail later, but basically we have a natural superposition of states coming out of the cesium reservoir, goes through a preparation state. After the preparation state, it goes into the cavity where we actually change the state of the spin of the atom. And it's actually effectively two different quantum gates in this case, divided. And in between that, we have an induced superposition. So this is an example of how, we're already using it today. The one thing we don't do in any of our quantum clocks or atomic clocks today is we're not using entanglement. And I shouldn't really say that. There are some articles in the last year or so where people have been entangling two atomic clocks, but I think that's extremely experimental at this point. But if you look at the primary difference between an atomic clock and a computer, what you're basically doing is with the atomic clock, we're really worried about the precision of the gates. We're trying to get as precise as we can down here on either the electromagnetic or the optical frequency in order to make sure these things, the gates are doing what we want. Whereas a quantum computer is essentially focusing on the outcomes, right? It's trying to manipulate the bits to come up with solutions, whereas we're trying to make sure that we're being as, as accurate as we can on making the bits manipulate. If I look at an atomic clock, this is a fairly common, block diagram where you basically just have a quartz crystal oscillator. You may have some level of multiplication to get it up to that 9 gigahertz that I showed on the last page. And then you go into that physics engine. So whether it's a cesium beam tube or vapor cell, any of those types of things, you're basically sending in a probing frequency and using some means of measuring how close you were to the frequency of the physics package for the best resonance, right? You have some type of feedback or error signal that you then adjust proportionally back into the oscillator until you're actually at that very, very fine frequency that the physics engine gives it, right? Once you have that, you have this very repeatable periodic transition. And what you're doing is you can, maybe divide it, maybe go straight out into an RF output, but you can count the pulses on the RF output to get elapsed time. And then you can add in, a reference to get the time of day off. So, in theory, you could actually replace a physics engine with the word quantum computer. What's actually interesting is there's some quantum computers, I've talked to some of the quantum computer companies, where for a portion of their day, they actually take a real quantum computer. These are ion clocks with their ion computers. And they actually put them into an atomic clock for a portion of the day. Now, they can't compute during that time, but they can get themselves really good stability out of their $1 million machines. So this is so precise that it's been used to define a second since the 60s. We've been defining a second as a hyperfine transition of cesium. I'm not going to go through the full definition, but basically it's 9,192,631,770 hertz that we're using to define a second today, which is that hyperfine transition. We'll get into in a minute what it is. And we're just counting those. So just like this guy here, we're essentially just counting pulses, right? Except we're counting 9 billion of them per second. So, in theory, I could have renamed this this presentation here instead of 80 years, could have called it 23 quintillion cycles of unperturbed ground state hyperfine cesium. All right, so what does it mean when we're looking at a clock? Well, what clock people like to do when we talk about how stable the clock is and why something is really good, and this gets into that really fine bandwidth of an atomic cell, is we're really looking at 3 different parameters that are coming out of this cell or out of the entire system. One is a signal to noise, one is the resonant frequency, and the last one is the bandwidth of that transition. We put it into this formula over here that tells us what the frequency stability is over different gate times, right? So it's a fractional measure. Basically, lower means better. And as we go out further and further, longer gate times. So if we go from a second to 10 seconds to 1,000 seconds, what you basically see is that the parts start to, the stability essentially gets better until the point where it won't get better anymore because you're dealing with maybe some limitation in the physics package or in the electronics. One thing I often hear from people is, why does the stability get better over time? What I like to explain to people is, think about when you're sitting on a bench using a spectrum analyzer. It's the same thing. You're basically just averaging down noise until you hit a floor, right? So, you're basically, as you adjust your resolution bandwidth of a spectrum analyzer, the sweeps take longer. That's exactly what happens here, right? If you think of the sweep time as a gates, you always see that noise floor until you hit a certain point will get lower and signal to noise increases. And that's why that frequency stability gets better. There's better gate times. How does this affect timing, right? A lot of people, it's a nice, easy formula for physicists and clock manufacturers talk about Allen deviation, but it doesn't mean a lot to computer people a lot of times. They look at it and say, what the heck does this chart mean, right? How does it affect a data set? Well, this graph is essentially going to, assist you along the way of determining what your timing error is going to be during GPS outages, right? And it'll wind up limiting your transactions per second. I gave a discussion on this at the OCP Summit this year. Won't go into it too much, but here's a equation, a holdover equation at the end. And what I'm really showing is there's certain points on this curve that are going to dictate parts of your holdover, right? So let's say I had a 1 hour GPS outage. That's going to wind up dictating my timing error according to this point on my curve. The other thing is I have to worry about the servo loop. So how frequently I was steering to GPS while it was available. In this case, I chose a cesium that I was steering for a day as an example here. But these 2 points are going to significantly contribute to the stability of the oscillator when GPS is out and your time error. And that's why these graphs matter. This is an example. If you look at the OCP cap specification for references, they define a Grandmaster class G1 oscillator that holds 1400 nanoseconds for 24 hours. And you can look at different types of oscillators. I took some values off some data sheets and some personal knowledge on these to come up with, an OCXO can hold about 12 hours uncorrected. A rubidium oscillator that's on the OCP tap devices today holds about 50 hours. And if we replaced it with the cesium unit, it could do about 560 days. So what we really want to get into is how do we improve stability? Well, we essentially have 3 knobs when you look at the equation, right? We have the bandwidth, the signal to noise, and the resonant frequency, right? So we can reduce the bandwidth, we can shift the resonant frequency, or we can increase the signal to noise. And in order to understand how to do any of that, we've really got to go be with Ant-Man and go delve into the quantum realm to really start to understand this stuff. So I'm not going to go into what all the numbers mean, but basically all our quantum numbers are essentially eigenvalues of that wave equation I was showing before. And I've got a hydrogen atom right here that I'm showing. You can see a couple of things, or it might be easier to see in a rubidium down here. One is the nucleus itself is spinning about its own axis. Another thing is you have electrons orbiting around a nucleus, right? And this is a very simplified version of rubidium on a it doesn't really look like that, but it illustrates a point. You can see hydrogen up here. That's essentially a electron. It's moving around in a cloud, which is actually what it does. We can't tell exactly where it is, but it'll be at some point in that cloud when we make a measurement. And as we look down here with the rubidium cell, if I freeze it for a second, basically it's this property of having one outer electron. We actually control what's known as the MS number, which in turn defines this hyperfine level. And that number is essentially a spin. Get into essentially what that means. So when we have a spin on an electron, I'm showing it right here. The nucleus itself has a spin, and we use the right-hand rule. So we basically, just do the curve to define spin up and spin down. Then we have electrons that are also having their own spin about their own axis. Turns out that if you are in a anti-parallel situation, so if you have the nucleus spinning in one direction and the electron spinning in another direction, you're at the absolute lowest ground state energy. A little bit more energy is required to get that electron to rotate the other way around and have a parallel between the nucleus and the electron. Right now, if you want, that's essentially in order to deduce that type of transition. By the way, both of these occur very naturally in nature and are very stable. But to induce that, shoot these gigahertz frequencies, so like the 9 billion hertz I was talking about before. Now you can also send it up into other orbital shapes, right? So that's kind of like as opposed to just changing the spin, you're now moving it in energy levels significantly. And that requires optical frequencies, right? So now you're talking hundreds of terahertz. That's when you're really changing N, L, and S all at the same time. So different quantum numbers are being changed, whereas within a microwave transition, you're really only changing the spin status of those electrons. And because of this, because you can get these spin statuses, I'll get into this in a little bit, but they're actually used as qubits, right? You can actually, this defines a 0 and a 1, whether the electron is spin up or spin down in relation to its nucleus. So why do people use the spin rather than maybe use the optical transitions? Why don't we just hit the light and have it happen? Well, most optical transitions have extremely short coherence times, right? So they become decoherent very fast. If I hit this with light, kind of exaggerated, actually it's a gross under exaggeration. For hydrogen, that's only up in that other valence band for about 10 nanoseconds. Can't do a lot with that. So it doesn't really lend itself easily to being used as a qubit. Now there are dark state ones when you get into much more complex theories that might be able to get used. But, if I have a microwave transition in these hyperfine areas, it's actually, the decay from spin up to spin down is essentially 11 million years for a single atom when it's in a vacuum on its own. Now, if you have 11 million electrons or atoms, it's obviously going to happen a lot faster, which is what happens in a maser. But with one, you're probably not going to see a transition anytime basically, since dinosaurs. And the other thing that's nice about it is it's a natural superposition, right? We don't know until we measure it, because those two states are stable, if it's either up or down. Right? So it's essentially in a superposition. It's also very easy to change this, right? Through either microwave or optical manipulation. You can get it to change these states. You can hit it with a microwave, it'll change the spin, or you can put it up into an optical transition and come down. That might give it a certain probability of having a spin. So this is why we use these. These are very favorable qubits. Want to go over what those transitions, those interactions actually are. There's 3 of them. The first one's absorption, which is basically I'm absorbing an incoming photon from a spin down electron. When that happens, it has to be at this specific frequency of E = h nu for that specific element or particle that we're looking at. And it'll force it into the up position, and it'll actually absorb that photon, right? It's absorbing the energy that's incident from the case. This is what we use in lamps. It's also what we use in cesium beam tubes. The next one is stimulated emission. And what stimulated emission does is you can almost think of it like pool or something, where if you look at the incoming wave more as a particle than a wave, you can actually, it'll transfer its momentum over to that unit. And when it does that, it forces it into a different level, or that particle into a different level, actually shoots it down when it was in the excited state and it's moving to the unexcited state. When it does that, it also emits another photon at the same frequency. And if you do this in a resonant cavity like a maser or a laser, those 2 photons that are now coming out not only are at the exact same frequency, but they're coherent, and very quickly you get a cascading event. You have a nice, strong, coherent light source or microwave source coming out of a stimulated emission. And finally, we have something called coherent population trapping. This one's a little bit harder to explain in the classical world. You're essentially blocking any transition states from happening. This is where we really talk about quantum interference, the wave nature of some of these things in the wave equation. Turns out there's a destructive interference that if I were to try to, basically I don't know if I'm in the up or down state. So I'm in a quantum superposition on an atom, and I hit it with a, 2 different frequencies of light, where the lower one would transition the ground state and spin down. The upper one would transition the upper level to go up into the optical excited state. If the difference between those 2 happens to be the resonant frequency that would move the microwave on its own, I get this situation where instead of having a very high probability of them both jumping, neither of them jump, right? And my light goes through 100%. And this is what we use in small form factor And this one's harder to explain and why you have to really start to have some faith in quantum mechanics and quantum interference. This was kind of proved in math where people actually saw it. And then they said, hey, Schrodinger's equation says this should happen. And it did. And we're able to use that today. So just kind of going over one last time what's happening. I've got a nucleus, I've got an electron, I'm going to hit it with some microwave source, maybe a Wi-Fi transmitter. Only kidding about that. It just happens to have a lot of frequency bands we're interested in. But what happens is when it hits it, and it was kind of a subtle change. So focus on that electron again as we go through this, and it changes its direction about its direction of spin, about its axis. Specific frequencies that occur, they're all alkali metals. They all have one outer valence. For cesium, it's 9 gigahertz. Rubidium, it's 6 gigahertz. Hydrogen, it's about 1 gigahertz. We can also use ions, right? If we strip an electron, we can make ions that have essentially one valence electron as well, which is very useful in some cases because we can use the fact that it's charged. And, you know, as an aside, it's not really spinning because an electron's a charged particle, but it's interacting to the outside world. You know, the magnetic field, the electric fields, things interact as if it is actually spinning. So you can imagine it essentially, you know, in the case of a maser, you could imagine if you hit the Earth with the maser as it's rotating around its axis around the sun, you'd actually cause the sun to rise in the west and set in the east. It's essentially what we're doing here by the spin reversal on the electron. Right, so on the flip side, when we do optical transmission absorptions, looking at what those frequencies are, and I tried to get the colors right based off of, you know, looking on the internet and stuff. So we have other transitions. We have essentially with them about 385 terahertz for an optical transition called 2-photon rubidium. So we got Darth Vader with his red lightsaber here. And then the other common optical clock today that you see is a molecular iodine clock. It's at 570 terahertz. So that's Luke Skywalker's green lightsaber. So, you know, these two guys can battle it out here. We also use aluminum. And what's interesting with aluminum is it's all the way up at 1.12 petahertz. It's outside the visible spectrum. And there's some really neat stuff being done because we can cause it to move, but we can't tell if it moved or not, right? In the optical domain. We don't have things that readily do it. So they actually have things called quantum logic gates where we pair it with another ion, and in this case, calcium, where we're actually looking for fluorescence at 411 terahertz to tell us if we manage to induce an optical transition. Some other issues about instability, other than just that nice equation I gave you, there are some other things that go on that also degrade our atomic clocks. One is if you look at the orbits, you know, in a vacuum with no external fields, you know, they'd be very well defined. We've got ground states here, we've got excited state here from an optical transition. But what happens is, and so we know what these are hypothetical transition frequencies. Call it unobtainium if you want. It's just an imaginary particle. But you can see about where the accuracy is based off of the operating frequencies here. There's transition frequencies of the gigahertz versus, you know, the terahertz. Got 5 orders of magnitude bigger here between that and the decimal place, even though the lower number is about at the same point. What happens when I put them into an external electric or magnetic field is the orbitals actually change. The sizes change, right? They get bigger. You actually have electrical dipoles here. And so they react to electric and magnetic fields. And so they're going to become larger. And when they become larger, that essentially means that these differences between the states actually change. And because they change differently, because first of all, as they get further away from the radius, you actually have less of a deflection. But the other thing is you also have this issue where you have a much lower denominator, much larger denominator. You see that optical clocks eventually will be much more stable, at least in theory, than a microwave. Other things that cause instabilities, one is thermal motion, right? If that particle moves, you can see here the frequency was originally green. I have to redshift it to get it on frequency to cause the same shift if it's moving against me due to the Doppler effect. Essentially, it's moving away. I have to decrease the speed that's going to do that. And this can happen, so this motion is the result of Doppler shifts that cause some instabilities. And there's, just the raw first order. And there's also relativistic ones you have to take. And you also have distributions that are also going to contribute then to the overall instability. Other things that cause instabilities, or collisions, right? So whether they're between particles, hitting a wall, or a photon hitting a unit, a background photon, let's say, because you have black body radiation, all these things essentially degrade or make my decoherent state. They basically pop me out of the state I want to be in. There's some energy lost. So these are things I have to worry about when I have an atomic. So there's a lot of different atomic clocks. I'm not going to go through all of them. We don't have time for that today. But basically, you can break them up between microwave, which is everything above the line, and optical, which is below the line. And I'll start talking about vapor cells. Is there a question there? Basically, with vapor cells, these lend themselves to very, very small packages. So things that, wind up fitting in 1 inch by 1.5 inch square. So the cells themselves are much, much smaller. They're on the scale of millimeters. They're relatively small size, low power. Basically, they are atomic clocks that use they put in a little small glass cell. They'll put in nitrogen or some other buffer gas along with the main element. And that's done so that there's less motion in the rubidium or whatever the element happens to be. And also it prevents some of the wall collisions. So it's a couple of ways of improving the stability of a very small form factor clock. We use coherent population trapping in small form factor clocks, particularly in the CSAC. This is where I talked about, I'm going to excite it at what should be the exact right frequencies. But if the delta is the microwave frequency of the transition, I actually won't have either of them go. There'll be no light absorption. So I'm doing that here by modulating a laser. And when I have no light absorption, I have a maximum amount of light detected on the other side of my cell. This is an example of quantum interference happening. As you go through the math, you actually have this interference. This happens, right? So this is essentially like a quantum identity game, right? Because I don't know what I had before. I was completely unable to affect it, and I don't know what I have afterwards. But even if I did know what I had, if I had a 0, it would stay a 0. If I had a 1, it would stay a 1 in these cases. This is showing, the CSAC Allen deviation. Does about 1 e to the minus 10 at a second with a bandwidth of about 1300 hertz. And the CSAC, which is the smallest chip scale, smallest atomic clock currently commercially available on the market, suffers from a fairly large line width due to the really small cell size. I'm going to next talk about MODR. This is microwave optical double resonance, which is what we use in slightly larger clocks like rubidium lamps. It's actually also used in conjunction with CBT and ion clocks as well. But basically, if I let the animation go through here, I borrowed this from Robert Lutwak. If I have a superposition of 2 different states down here in the bottom in the microwave region, ground states, and I hit it with a narrow band optical source, I can cause only the F equals 1 state, in this case, to jump up to the excited, right? The 0 states won't move. So if I do this a couple of different times, by the way, when it decays, it has an equal probability of going into either state. If I let this play out several different times, eventually I depopulate that upper state, right? The 50-50 probabilities work out to the point where all my electrons are now of all my different particles are on that ground state, right? Then I come along with a microwave resonance that would essentially move it back, from spin down to spin up with the exact right spin, the exact right frequency. So with an MODR unit, what I'm doing is I'm actually trying to, make the most light absorption, trying to get as many as I can back up here. As I'm hitting it with a light source, I'm trying to pump them using a microwave source back up into state 1. When I get the exact right frequency, I'm going to have a maximum light absorption in this case. So if I look at these optical transitions, for the hyperpine point of view, from these 2 ground states, essentially, I was taking, doesn't affect the zeros, right? So 0 doesn't move for an optical one. For a If I was up at state 1 or the positive state, it's going to go either way or, right? And then the microwave only winds up transitioning from 0 to 1. So this is an example of how to look at these things. It's called logic gates. And this is the implementation of this. Again, don't have time to fully go into how these work, but the bottom line is there's a light source, there's a microwave excitation source, and I'm looking for a minimum amount of detection at the end of the clock source. So if I look at an example of an MODR or a lamp type of unit, I get actually really good signal to noise, really good 1 second ADA, 2 times 10 to the minus 11 at 1 second is actually as good as a CBT. Where these don't wind up working is when you get out to these longer times, there's other things that wind up limiting it. There's drift that winds up on a month, you see anywhere from 1e to minus 11 to 1e to minus 9. So it's not as inherently stable as a CBT, which we'll get into, doesn't have any shifts. But so I'm limited in these solutions by things like collisions with atoms, other atoms in the walls, background light noise. If you think about it, while I'm hitting my microwaves, I'm actually hitting my light the whole time too. So there's some interaction there. The stability of the lasers that are causing the jumps, and then finally the thermal motion, they're moving a lot. So another solution then is to go to a beam tube type situation. This was what I showed earlier, got cesium hanging out over here. But basically I have a heated reservoir of cesium that can be in a superposition of spin up, spin down. As it comes out, it goes through the first magnet, which is essentially doing a state preparation. It's kicking out one state while keeping the other. And then it's going into the microwave cavity. And what you can see is it's going in twice. These are actually, they're called pi/2 Rabi oscillations. The bottom line is what we're doing here is we're actually in the first cell, we're putting it into a superposition state again. Then as it goes through the second cell, we're actually separating things back out, and then it goes through a magnet to separate it again. Turns out this is almost like an interference, if you can imagine a 2-slit experiment, except now we're doing it in a time domain instead of in the XY domain. And the distance between these two cells is what determines my line width, right? So you can see here the dimension of the actual microwave cavities determines one bandwidth, but then I have this interaction of the two of them that's determined by Y, which is the distance between those two. This does about 2 times 10 to the minus 11 as well, but the difference is the noise continues to go down out past 1,000,000 seconds, and then it never rises. So cesium beam tubes have absolutely no drift at all, right? So there's no frequency drift over time, at least not a deterministic one. So now we're limited on a beam tube by, ironically, something that was designed in 1922, which is the size of a 19-inch rack. That's defining my cesium beam tube length. So for commercially available cesium references, that 19-inch is the biggest source of controlling my land width, my stability. I can make it longer, and I'm oversimplifying it because you do have to worry about homogeneous fields and some other things. But really, if I made it twice as long, 4 times as long, it could be more stable. And that's what NIST used to do for years in other places. There are also relativistic effects and velocity distributions. And there's also, the signal to noise at the end is ultimately, it's limited by the actual noise created by individual atoms hitting the receiver. So how do I improve on a CBT? Well, one way to improve that and get even better noise, better stability, is to move to ions and ion traps. So what ion traps enable me to do, and there's an example of a Paul trap here, is it allows me to take a whole bunch of particles and get them into this one area in space because I have an electromagnetic field around it. I can actually force them into a cloud. I can get like 1,000,000 ions in one little cloud. And getting that many in one small area gives me a very high SNR, which helps for stability. But also, they're now in this cloud as opposed to moving across a beam tube with not a lot of motion, right? So I've reduced the motion and stability by putting them in an ion trap. And then the other thing that happens is, because I'm not limited by the 19-inch rack anymore, actually the way I interrogate these is by sending a microwave pulse through them. And I can have a very, very small line width from an ion trap. them because I can really interrogate these things for a much longer time. Whereas with the cesium beam tube, it was the time of flight of the electron or the cesium atoms across that tube that was defining. How does it work? It's a little bit different. I won't get into all of it, but essentially, it's another example of microwave optical double resonance. We have a resonant frequency between the lower two ground states. This time it's at 12.6 gig. I hit it with a microwave pulse that's on the order of a second, maybe a half second, or 100 milliseconds. Just depends what geometries and what I'm trying to achieve are. That forces it up to the F1 state, which then causes it to get optically pumped. And as I sit there and hit it with the optics, what I'm trying to do is create a situation where I detect a minimal amount of light on the other side. There are some complications of using a terbium like this, which is that instead of just falling down back to the ground state, it'll also fall off to one of these optically dark levels I was talking about before. And actually, this is another reason why terbium ions are very popular, is they have these dark spaces. Don't want it for an atomic clock, but it allows me to make an optical qubit for a quantum computer. So I also have to pump these out of this optical dark state though, to get them back into the main MODR region. So this is an example of what they look like. Closed loop, I'm looking at about 8 hertz. In this one, you can think of, it is a couple of different quantum logic gates again, right? I have an optical 0 to 0 transition. I have a microwave 0 to 1 transition. So it's a couple of different gates. And in this case, I'm doing somewhere around half an order of magnitude better than a CBT can do. I'm down at about 2 e to minus 12 at 1 second. And okay, so how do I get something even better? Well, the next step along the path is laser cooling, right? Laser cooling is kind of neat. Basically, it's taking a quantum principle of hitting something with light, and that photon, even though I'm showing it as a wave here, has momentum, right? It's going to hit a moving particle, and it's going to absorb it. That particle will absorb the photon and then scatter it off in a random direction. So if I continue to hit it with a laser in one direction, it'll eventually slow it in the direction that you're moving towards the laser. And I have the laser blue shifted in this case, simply because the Doppler effects is I actually have to be at a higher frequency than the natural transition frequency to do this. But this allows me to get even slower, much longer. It actually gives me the opportunity for single ions. There's lots of neat things I can do on these to improve Q. Just one example of a laser cooled ion trap part that I'll just give you is this cesium found right here that's laser. Little motion here showing at the very beginning of it, it's laser cooled, and then one laser is pushing it up, and then it just falls back down by gravity. Very long interrogation times and also much more stable. So this guy has about 1 e to the minus 13 stability, goes down to 1 e to 16. This was the primary standard for a very long time. And this is giving a summary of the microwave clocks, just quickly getting into some optical clocks. All right, so we talked about a couple of different things, but what's nice about optical clocks is if I move that resonant frequency 100,000, 5 orders of magnitude off to the right, I'm going to get a much smaller signal to noise ratio. And that's really what's in labs today. That's even, what's being rolled out in some small units today, but it's because of that transition that you're seeing these higher stabilities, right? So if I looked at what my atomic clock was before, I'm basically removing that quartz oscillator with the laser, which is still it was still an oscillator. So that's my local oscillator at this point. Now, instead of having to multiply up when I go into the physics engine, I actually wind up dividing down with something called a frequency count. That divides from optical to microwave frequencies such that I can effectively use it in electronics. And I can do that without a loss of stability. Guy who came up with this got a Nobel Prize for it several years ago. So that's really the big differences is, the laser, the frequency cone. Physics engines are different as well. But I'm just going to give a couple of quick examples here. Rack mount optical clocks. There are a couple of companies today that have announced clocks. They're not really in production. They've got very early on anyway. They've got some samples out or they've got demos out, but nice products, right? They're either 2U 19-inch rack up to a 4U19 track at the very beginning of their life cycles. And what they use for optics is they're not, they're taking advantage of commercially available lasers. So these aren't exotic lasers with very tight bandwidths. But what they're doing is they're using these lasers with physics essentially setups that let me use the very high frequency and the very high, SNR that I get from these types of applications. But the bandwidth is also very large compared to an atomic clock. So in the end, you don't get 5 orders of magnitude, you get 1 or 2 orders of magnitude better than a beam tube. These also have drift rate issues that are continuing to be worked on. But whereas a cesium beam tube has no deterministic drift, these are going to drift not as bad as a rubidium oscillator that I was talking about earlier, but probably along the lines of a maser or something around. So they do have some deterministic drift. And this is just, I'm not going to go through the chart, but for your reference, this will be available afterwards. These were taken off websites or previous presentations that I attended. You get a rough idea of what these look like. I'll also quickly talk about the most stable optical clocks that are still in labs out there. One is laser cooled ion trap quantum logic clocks, right? In this case, we're completely isolating its aluminum. It's a little bit hard to see here, but this was the 1.12 petahertz transition I was talking about. We can't even detect that today because we don't have really good systems to do that. So we have a single ion in there and we've basically frozen. I mean, it's really, really, really cold. And then we put a magnesium or calcium ion in there with it. And that, essentially couples with it. It's not quite entanglement, but it will tell us the state of the aluminum. So this is my actual atomic resonator, the aluminum there, but I need either magnesium or calcium to detect it. What's interesting about this arrangement, if I did this with the terbium, guess what? That's a qubit. That's the reality of a qubit right now, right? So it's just this is what people use for qubits. On the other side, people aren't really using this, but you can also do strontium optical lattice, which are pretty exotic, really cool. Both of these get you sub 1e to the minus 18. The one on the left has a very low SNR because you only have an individual ion, but it has incredibly tight gamma and very high operating frequency. So we look at the strontium lattice, it gets you still a very small band, but not as small as one on the left, but it has a high SNR because you put essentially these ions into this arrangement of a lattice where they're forced into these very low energy states all next to each other. So that's it. And I'd like to say thank you for your time, or since I make atomic clocks, you should be saying thank me for your time since we made it, right? Sorry, a little bit not humble there, I'll say, or arrogant, but it's always a good little line to put it.
Amazing. Thank you very much, David. Wonderful presentation. Okay, let's open the floor for questions.
Yeah, this is the first time I've considered synchronization. Like I normally consider it as kind of a quantum sensor, but I've never considered actually getting work out of the process. So are you share your slides or something so that we kind of reread and rethink about all of this? Because it's a lot.
It is, and it was in an hour. I tried to put a lot together. They'll be shared after the presentation. You can look through it. I can put a couple of articles up there that I read. Believe me, I didn't know anything about quantum computers before I decided to put that twist on this presentation. So I've been reading articles for the last month and talking to a couple of people to try to crystallize this all in my mind too.
Thank you.
You're welcome.
It's a good presentation. It's a lot to think about.
Thanks.
Any questions, any comments? Maybe I can ask like a question, like with regards to entanglement, how do you see that like coming together, let's say with synchronization? Like, don't we consider, let's say, you've seen, like, I use this term like loosely, like pseudo entanglement, right? I keep saying, like, when you have synchronization, that's like a pseudo entanglement, because
Yeah.
if you timestamp an event with two clocks that are synchronized, you should get the same value within the, again, the window of uncertainty. So how do you
Yep.
see this all coming together?
So honestly, there are some papers out there right now that I gotta admit, I don't fully understand how it works. It has to do with entangled photons, but there's been some work with single ion atomic clocks where they've added in entanglement to it. So the individual particles are entangled that they're using for the atomic clocks. And what that gives you now is now you suddenly have an ensemble of two clocks that are truly locked together, as opposed to us being in this situation where we're doing other things to try to tweak them to say, okay, I know where I should have been. Here's the timestamp. Let me make my adjustments and make everything happen. They're truly getting to the point where it is raw synchronization, right, between the two. And that actually then improves the ensemble characteristics you can get out of, ensemble clocks will actually be higher. It's pretty far out stuff they're just working on, but I think that's eventually what you'll see in a number of national labs is you'll actually see they're going to take several of their clocks for their ensemble right now, which is essentially a lot of paper and stuff, or these measurement systems. They might eventually move to entangling all their different atomic clocks. So
like basically, like this traditional synchronization is nothing but tracking. And
yes,
then we will have, let's say, with entanglement, truly, let's say, synchronized clocks.
Yeah.
But then at the observation, you have the error that you get because you need to, let's
exactly.
say, interrogate whatever
Yep.
is.
Yeah, I mean, ultimately, there's some advantages to entanglement that a lot of times you can say, well, what good did it do me? I can't get any information out of it. But the thing is, you can actually do computations, just not look at the results. It's kind of like the whole quantum computer idea. So it's interesting. Actually, Hisham, thank you. He posted the article about it where they had the two quantum clocks that were entangled. So it's I think that will eventually, it's not going to be, this is way out. Not something we're going to see in 2 or 3 years.
But this actually
Probably
solves a lot of, let's say, these applications that we are essentially looking in this, interest group that we have here, that like in computation, let's say you want to have an alignment, like chronological alignment, let's say between processes and so on. And let's say with the speed for CPUs, let's say, I don't know, it's kind of capped right now. It's like 5 gigahertz or something like in consumer, but data centers are still under 5 gigahertz. Let's say 200 picosecond, and then you want to go, let's say, avoid aliasing. So 100 picosecond, it's still like very tough, let's say, for PTP. So like
it's incredibly tough.
yeah, so you have to look for something. And then let's say if you want to, I mean, there are things like, for example, the limitation you have with latency, but again, that's for a distributed system. But if you want to reconstruct the let's say the chronological order, that's not necessarily a distributed system anymore. So that's why you still need better than latency. And I see like this perhaps can be a solution, because I mean, in implementation, it should be, again, instead of a grandmaster, now you have, let's say, a laser that is providing the beam, and then you have the split somehow happening, and then you get to different units, and then these different units are entangled. I mean, this is key distribution, quantum key distribution. So then you do the interrogation there separately, then probably you can hit like this, let's say, sub 100 picosecond precision, right?
I would think you're going to get into the picosecond, very possibly, right? Single picosecond type numbers.
That's great.
There's actually, I think you might have had them on. They were talking about quantum time transfer. Who was it? Cyrus gave a discussion previously.
Yeah, the problem is there's a floor on accuracy, right?
Yeah.
Because of uncertainty. So
I mean, we're way far away right now. I think I'm sure physicists and are going to figuring this stuff out. Though.
Yeah. One thing about like this quantum, entangled based, let's say synchronization is you're not gonna have accuracy, you're gonna have precision. I mean, because
Mhm.
you're in the raft of that laser that is putting there and start from your own epoch, which is
Yep.
great. I mean, you really don't need accuracy in the case of this alignment of the let's say events. And then eventually you can have one of the machines that's connected to some sort of a UTC, and then you have now an entire projection of that raft to the reference if needed, like
Yep.
Bijan, I guess we have to start that, right?
I was just thinking, here we go with out of order events.
No, it's just your raft, right? Right. Your raft can be handled separately, and I mean that's literally what the time card does. Time card brings basically the accuracy to this system that is already precise, which is based on PTP, let's say, or White Rabbit or something. And time card is like, okay, I'm taking the top node and I'm synchronizing with UTC, and now everything else is supposed to get the precision, sorted. So
I think, Ahmed, this is Ramki. I think the challenge is going to be the software because
Yeah.
most of the missions are in the cloud.
Yeah.
And so these are EC2 like instances in all in the cloud, elastic computing. You can have the best quantum clock. How do you transfer it to the stack and run the applications and workloads that can bring it below a microsecond? I think you saw some announcement from Amazon a couple of weeks back that
Mhm.
100 microseconds. So I think software is going to be the challenge, and that has to meet the quantum technology at some point at the crossroad and help solve the real accuracy issues. That's kind of the practical difficulty.
What I'm excited about is probably not what you intended, and what I'm excited about is like this kind of turns everything inside out if you think about it, because this the medium in between, the 2 points, from detection points could be what you'd think of as a network, right? And so
Mhm.
now you have this quantum network between different elements, and now we can get work out of it, so the network can do the computing. It's very strange. You know then what's the point of the computer?
Yeah, I think that's the reason I said we may have to look at this from a different angle, not solve the problem traditional methods and come at a different angle, like you said, so that you can address some of the bottlenecks that we are dealing with today, achieving sub-microsecond, nanosecond synchronization in the cloud.
And the other interesting aspect of it is that, given what you can do in the quantum realm with entanglement and so other things, it adds a new dimension to distributed computing, and kind of what Ahmad was referring to with this, kind of high precision, this could be a very high precision system. But um, you know, if you think about some of the implications of it, I mean, this could be very very game changing. I'm still kind of wrapping my mind around it, but
So,
because you could actually literally have like maybe this becomes each node becomes a qubit, right? And so this system is actually connecting all the qubits together. It's very interesting.
so, what quantum computers today have a lot of different qubits all interacting. They can do entanglement on those qubits. Um, and the real benefit, for something like AI, that you could model it eventually, is this idea of being able to do multiple paths at once, and then the interference pattern actually collapses the solutions that are least likely to happen and reinforces the ones that are most likely. That's why iterative things like that actually lend themselves to it fairly well. And that's why something like AI, this could be, something that's really going to help speed some of it up. But it's really, having read through a lot of the articles right now, it's really ones that aren't necessarily depending on time-based answers to get there. But the qubit itself is essentially described by 4 complex numbers. And even though it's in 0 and 1, where it is and its probability before it collapses is described by these 4 essentially continuous complex real numbers. And that really is what frees up this whole idea of, gosh, I can get so much more information. You know, if I get 2 qubits, I now really have 4 complex numbers that are delivering information, as opposed to when I look at 2 bits, I've only got 2 real numbers, right? So that's where this exponential processing, and I got to be honest, I don't understand how the algorithms work. You know, I tried to do some brushing up on that and said, yeah, that's for another day when I want to let my mind explode. But they're using it, right? There are companies, you know, Microsoft, you know, I think AWS actually have access. You know, you can get access to a quantum system. And these types of iterative, hey, how do I get a businessman to get to the 20 cities as fast as possible? What's the best route? Those types of things apparently are what these do really, really well, which is also something that AI does really well, right? So there's definitely a confluence here.
Wonderful. All right.
Only problem is I think like I think I saw 100 or 80 qubit computer right now costs about $900,000. So
That's nothing for Jan's world, right?
No, in OCP dollars, it'll be much, much less.
In OCP dollars, that's nothing. Fraction. All right. So we are on top of the hour. I hear anyone wants to say something? Sorry. So that was just an echo. All right. So okay, that's a wrap for 2023, I guess. And we'll see everyone in 2 weeks next year, right? And we'll have a presentation by Judith Olson from Quanta about precision timekeeping application discussion for optical atomic clocks. So it will be basically continuing on that, like the cone blazer and whatever you can do with a commercial product, basically, that is coming from Quanta. And yeah, that's it. I think that's a wrap.
Consider putting a review or a second meeting in the books, a follow-up for this.
For sure, for sure. And again, as usual, the recording and the slides you can find them on the wiki, which you can reach out also via ocptap.com. All right.
Right.
Thanks, David.
See
Thanks,
everyone.
guys.
Bye-bye.
Bye.
Bye.